Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is an introduction to renewable energy. Our objective is to perform a brief introduction to a subset of the various forms of renewable energy being used for industrial and small-scale electrical power generation. Specifically, we'll take a quick look at wind, hydro, and solar and discuss the features and advantages and disadvantages of these renewable resources. A couple housekeeping notes before we begin regarding the intended audience and the scope of this and related lectures. Bottom line up front, renewable energy technicians are electromechanical technicians, and these lectures on renewable energy are not intended for the average dimwit bebopping down the street, but rather viewers with the necessary background and working understanding of energy, power, efficiency, capacity factor, DC circuit analysis, single-phase AC circuit analysis, three-phase AC circuit analysis, the three dimensions of AC power, apparent, real, and reactive, power factor correction, transformers, mechanics, hydraulics, switches, sensors, hardwire, relay-based ladder logic and motor control, programmable logic controller or PLCs, digital logic, industrial control, power electronics applications like rectifiers and inverters, batteries, power transmission, and motors and generators. If there is the slightest hesitancy on your part about any of these subjects, by all means revisit the supporting content in the Big Bad Tech channel, because when I discuss renewable energy, I'm operating on the understanding that we're all on the same page regarding electromechanical technology, and we are moving forward from this agreed upon start point with all of these tools in your toolbox. This being said, if you're a little rusty on any of these topics or feel a little overwhelmed, don't worry, I got you. Because as specific topics come up in the course of this discussion, I'll try to point you to the correct lecture or playlist that explores that specific topic of interest in greater detail. Regarding the scope of this and related lectures, we will examine solely the electromechanical concepts of renewable energy, not chemistry, biology, economics, politics, nor public policy. This means I'm not going to go into a lot of great detail about the chemical reactions in biofuel processing, nor discuss the economic impacts of production tax credits. But when it comes to something like the electromechanical aspects of wind turbine blade pitching mechanisms, quite like Teddy Roosevelt and his stupid bears, I'm going to talk your ears off. I do need to place special emphasis on the rules of engagement regarding politics, since for some inexplicable reason, renewable energy has entered the oh-so-productive culture war. If you want to talk politics, go right ahead, but don't do it here. Go shout at an Arby's clerk. This is the internet, after all, and we need to keep it free from sensationalism and be polite to one another as its founders intended. I will not engage in political discussions, and neither should you, because you can't out crazy, and there is some cray stuff out there that has no basis in reality. Renewable energy is not a government conspiracy to take away your guns and turn you into a gay. Trust me, I've worked for the government before, and they are straight up not that smart nor that organized to pull off a scheme of such complexity and dubious worth. Renewable energy is happening, whether you like it or not, largely because it's driven by economics. Let me ask you this question. What is the price of fossil fuel-based non-renewable resources like gas done over the course of your lifetime? Yes, there are short-term fluctuations up and down due to market volatility, but long-term, inevitably, the price of gas has gone up and it is not going to go down. More people siphoning off more gallons from an increasingly less accessible pool of limited resources. You do the math. It's simple supply and demand. The reality is the price of fossil fuel-based non-renewable resources has gotten to the point that installing and maintaining renewable energy facilities is becoming cost competitive. Yes, renewable energy installations cost money to install. They require regular maintenance, have inefficiencies, and have negative impacts just like every other power station out there. But the fuel is free. You know renewable energy is the real deal when big banks and multinational oil and gas companies make huge investments in it because they recognize the future of renewable energy is profitable. The long-term price of fuel is just one aspect affecting supply and demand economics. From the demand side, consider large new customers requiring copious amounts of electricity, like data centers, crypto mining operations, and AI, and perhaps most critically, the electrification of transportation. Switching from a petroleum-powered transportation infrastructure to an electric-powered one will be a fundamental change to business as usual and will place a heavy new demand for electricity. From the supply side, consider that the planned retirement of numerous coal and gas power plants will remove these producers from the supply. Additionally, consider the impacts of the increased frequency and intensity of extreme heat events and wildfires that interfere with the generation and transmission of electrical power. As demand increases and supply decreases, the slope of the supply and demand curve only gets steeper and steeper, and renewable energy makes more and more economic and practical sense. Lest you become too enthused, let me inform you that renewable energy is not magic, and one preferred source cannot immediately solve all of our problems overnight. Solar power is not the solution. Wind power is not the solution, nor is hydro, biomass, nor geothermal power in isolation. All these sources taken together, including natural gas for an interim period or even small modular nuclear reactors, and the necessary means of efficiently transmitting and storing these diverse energy sources are. A non-technical associate of mine perhaps put it best. Think of every energy source as a piece of Swiss cheese with obvious holes that prevent reliance on that single source. Take another piece of Swiss cheese with its own holes in different locations and overlay it on top. Less holes appear in the layered mass. Add more layers, and pretty soon there's no holes. A more diverse energy portfolio might ultimately be cheaper, more reliable, and more secure, but it will take time, investment, and an educated workforce to make it happen. It won't be easy to build, it won't be simple to manage, and I never said it would be. By virtue of watching this lecture, I'm presuming you are interested in becoming part of that educated workforce and the new energy future, rather than just bitching about how hard and complicated it's going to be. So let us begin. We should probably start with some necessary definitions. First, let's differentiate between non-renewable and renewable resources and identify a couple examples of each. A non-renewable resource is some resource that is finite or limited in quantity and not replenished within our lifespan, meaning what you got is what you get, and you ain't getting any more, so tough luck if you used it all and had no backup plans. Coal, oil, and natural gas are examples of non-renewable resources because there is simply a limited finite amount of these fossil fuels available, and it's not cost-effective to raise a dinosaur from a hatchling to adulthood, only to kill it, bury it, hopefully in a more convenient and accessible location, and wait till the combined heat and pressure of the Earth turns it into a usable petroleum product. By the same definition, we should also consider nuclear a non-renewable resource, since within our lifetime there's no chance of being resupplied with nuclear fuel, and although there's a substantial amount of it out there, it's still a finite quantity. A renewable resource, in contrast, is continually replenished by ongoing natural phenomenon. Solar, wind, hydro, biomass, and geothermal are renewable resources because these resources have, are, and will continue to exist for the conceivable duration of humanity's future, whether we use them or not. Renewable resources don't run out and are cyclically replaced in perpetuity. Let's now differentiate between dispatchable and non-dispatchable resources. Dispatchable generation refers to power sources that can be started, stopped, and adjusted by grid operators to match electrical power supply with electrical power demand. Examples of dispatchable generation includes coal-fired power plants, natural gas plants, geothermal plants, and large hydroelectric facilities that can quickly ramp up or down depending upon the grid's needs. A nuclear power plant is also considered dispatchable. However, they're not exactly the most responsive of beasts and can take a long time to bring up to full capacity. Non-dispatchable generation, in contrast, refers to power sources that cannot be started, stopped, or adjusted at will due to factors that cannot be controlled. Non-dispatchable resources tend to be intermittent, which means they're not continuously available and can disappear as suddenly as they appear, and variable, which means their intensity isn't constant and can spike up or down due to factors out of our control. Examples of non-dispatchable generation include solar and wind, both of which are highly dependent upon the weather. I should note that non-dispatchable does not mean unpredictable. Admittedly, we don't own nor can we control the weather yet. We can, however, predict the weather to a reasonable degree of accuracy and take this into account when forecasting fuel requirements for the near future. With a diverse portfolio of resources at your disposal, you can make use of cheap and plentiful renewable resources when they're available and only resort to more expensive non-renewable resources when they're not. Like I said earlier, economics is largely driving this fundamental change. Here's a plot of energy generation by source for a period in early spring 2024. You'll note natural gas generation in tan experiences a dip. Why? Well, take a look at wind power in green. It's peaking. If we zoom into a period towards the end of March, you can see some pretty predictable behavior. Solar in yellow, peaks and valleys as the sun rises and sets, with changes in intensity from one day to the next. Nuclear power is steady as a rock. Coal, hydro, and natural gas ramp up and down as electrical demand peaks during the day and valleys at night. When free renewable wind power peaks, non-renewable natural gas turbines back off. This balancing act is not without its complications, though, since, as I mentioned earlier, non-dispatchable resources can be highly variable in nature. Imagine a sudden, unanticipated ramp-up in demand in which large numbers of customers suddenly need more power, accompanied simultaneously by a sudden unplanned ramp down in supply, when a regional weather event suddenly flatlines the outputs of large numbers of solar and wind farms. Too much demand, not enough supply, and it all happens too quick. As we learned in the Power Generation, Transmission, and Use lecture, way back in the DC Electrical Circuit Analysis playlist, available at the Big Bad Tech channel, the grid is a just-in-time delivery system, meaning instantaneous power supply must at all times match instantaneous power demand, and lacking energy storage, which we'll discuss in a moment, any imbalance between the two can mean catastrophic failure. Consider the opposite scenario, a ramp down in demand accompanied by a sudden simultaneous weather-induced ramp up in supply, where all the solar and wind farms are at peak capacity. Too much power and nowhere to send it. Without any load to direct this power, this output needs to be curtailed, which is essentially turning off excess generation to meet low demand. Lacking storage, curtailment represents a lost opportunity because all that free renewable power is essentially going to waste. These scenarios illustrate the fundamental requirements towards developing an all-renewable grid. In addition to generation from renewable resources, we need to consider storage, transmission, efficiency, and effective intelligent management. Energy storage. During periods of high supply and low demand, free renewable energy can be stored in pumped hydro facilities, batteries, flywheels, compressed air facilities, and/or converted into and stored as a combustible gas like hydrogen. During periods of low supply and high demand, these stored resources can be drawn down to balance input and output. Lacking storage in all renewable grid will be unreliable and unworkable because solar only works when it's sunny and wind only works when it's windy. Transmission. A modern transmission system would allow the export of free renewable energy from regions experiencing high output and low demand to those regions experiencing low output and high demand. Long story short, it may not be sunny or windy at your house right now, but it is sunny and windy somewhere. Efficient interconnection between distant regions allows those regions to share excess production with their neighbors and rely on those distant neighbors in times of need. Additionally, the most productive sources of renewable power tend to be some distance from where the power is actually used. To get that free renewable power across the barren wastelands where it's generated, to the shoe-wearing regions of the country where it's used, you need a modern transmission system. We'll examine high-voltage DC transmission in later lectures, which enables efficient power transfer from point to point over long distances. Efficiency. Viewers will recall that more efficient devices use less energy to accomplish the same task. A society using more efficient devices does not need to generate as much power, since less power is directed towards losses. Intelligent management. We'll explore smart grid applications in later lectures. However, one component of the smart grid is known as load shifting, which starts or stops an electrical load as a function of supply. Consider a smart appliance like a dishwasher. Load the smart dishwasher before you go to sleep or go to work, and you press start. You don't care when the dishes get washed as long as they get washed before you wake up or you get home from work. The smart dishwasher sits there and waits and waits and waits until there's a lot of inexpensive renewable power in the grid, and then and only then starts the cycle, thus freeing the utility from resorting to more expensive non-renewable resources. Now that we've got some basic definitions and concepts out of the way, let's take a closer look at the different types of renewable energy on an introductory level. You'll note this lecture largely concerns itself with the production of electrical power from renewable resources rather than the direct use or use as energy storage. Perhaps one of the greatest advantages of an electrical power grid is that electrical power can be so easily converted to other forms at the point of use, some distance away from the initial source. For example, if a warm house is your intended goal, one could directly burn wood, a form of biomass, in a wood stove. One could also appropriately site your house such that it experiences longer periods of passive solar exposure, or if you live in a geothermally active area, directly pipe geothermally heated water through a radiator. Using these renewable resources in this direct fashion results in the desired outcome of heat with no intermediate conversion stage. Wood biomass to heat, sun to heat, geothermal to heat. Problem is, not everyone has a wood stove, not everyone's house is properly sited to take advantage of passive solar heating, and not everyone lives on top of a geothermal hotspot like those shy and reserved inbred blonde elves that populate Iceland. For this reason, resources are often converted into another form, typically electricity prior to being used. Biomass to electricity to heat. Solar to electricity to heat. Geothermal to electricity to heat. To be sure, there are losses in this two-stage conversion of these resources, but it sure beats having no heat at all. Historically, electrical power generation has involved some prime mover using a turbine to turn the rotor of a generator to export electrical power for use. A prime mover is some outside mechanical power source that could take the form of expanding steam, falling water, or moving wind. In this fashion, the mechanical power of the prime mover is converted into electrical power. For example, a coal-fired power plant burns coal to heat water in a boiler to produce high-pressure steam that forces a turbine to rotate. The rotating turbine turns a generator, which produces electricity. Historically, coal-fired power plants served as baseload power production. However, over time, coal's share of electrical power production has steadily decreased. A nuclear power plant operates similarly, in that the heat of nuclear fission heats water in a boiler to produce high-pressure steam that forces a turbine to rotate. The rotating turbine again turns a generator, which produces electricity. As with coal, a nuclear power plant can serve as a reliable baseload power plant, although it's not the most responsive of beasts and sometimes struggles to track rapidly changing demand conditions. Combustion-style natural gas turbines operate slightly differently, in that natural gas along with a stream of air is combusted, and heat from the combustion itself causes the turbine to rotate. As with other systems, the rotating turbine turns a generator, which produces electricity. Natural gas plants are sufficiently responsive enough to be used as base and peaking power plants, i.e. plants brought online or disconnected at a short notice. Energy production from these non-renewable resources is reliable and dispatchable, but not without attendant disadvantages beyond their inherent non-renewable, i.e. finite nature. Coal-fired power plants are a source of CO2 and particulate emissions. Natural gas has significantly less particulate emissions and only emits about half the CO2 as coal, but it's not benign in any sense. Nuclear, in contrast, produces no CO2 emissions at all. However, spent fuel is considered radioactive waste that must be safely stored. For this and other reasons, renewable resources like hydropower, including wave and tidal energy, solar power, including PV solar and concentrated solar power, wind power, biomass, and geothermal are now considered as serious alternatives. You note I consciously try to avoid using the buzzwords clean or green when discussing renewable power, since they mean different things to different interest groups and are so overused and misapplied from everything from clean coal to green laundry detergent, they've largely lost any meaning to society. Now, before we dive into this clean and green list, I want to be upfront about the scope of this series. As fascinating as wave, tidal, concentrated solar power, biomass, and geothermal power stations may be, I probably won't discuss them in any greater detail beyond this briefest of brief introductions, and instead reserve future lectures for detailed technical discussions on wind, hydro, and solar PV for two very important reasons. Reason one, I do not have the same level of experience with wave, tidal, concentrating solar power, biomass, and geothermal power as I do with wind, hydro, and solar PV. Reason two, wind, hydro, and solar PV are where the jobs are at. I'm not saying there's no jobs in wave, tidal, concentrating solar power, biomass, or geothermal, but I am saying there's lots of jobs in wind, hydro, and solar PV, and this is where you need to focus your efforts on, at least initially. In keeping with this spirit, realize I'll be concentrating on large-scale industrial applications of renewable energy that can get you a job, rather than small-scale residential or off-grid applications, at least initially. Let us begin. Hydro. Hydropower harnesses the force of moving water to generate electricity. Hydropower is a renewable resource because it depends upon the water cycle, which replenishes our rivers from the snow and rain every year. Typical hydropower facilities include a dam that backs up the water to help control the river's flow. The reservoirs behind a dam are generally of one of two types: storage or run-of-the-river. As the name implies, a storage project uses a reservoir that stores a sufficient capacity of water for use when electricity demand is high, whereas a run-of-the-river project operates with minimal or no water storage. The The simple diagram of a hydropower facility includes a reservoir, a dam, an inlet, a penstock, a turbine, a generator, a powerhouse, and an outlet. The dam backs up river water. The inlet directs pressurized flow into a penstock, which is essentially a pipe or conduit used to carry water to a turbine. The turbine, of which there are two major types, a Kaplan, which looks like the bladed propeller of an airplane or a boat, and the Francis, which is a reaction-style turbine that works on fluid pressure changes as water moves through it. The turbine is typically mounted to a vertical shaft which spins the generator inside the powerhouse. Finally, the outlet serves to expel water from the turbine downstream. By the way, a real hydropower facility is a lot more complicated than this simple diagram suggests. There are a number of accessory components like wicket gates that open and close to keep pressure and flow, thus torque and rotational speed of the turbine and generator inside desired specifications. We'll examine industrial applications of hydropower production in greater detail in later lectures. I should note there are numerous alternate configurations for hydropower facilities and turbines that are often reflective of scale, head, and flow for a particular site. A popular design for smaller hydropower facilities is a Pelton wheel style turbine, which uses a nozzle to direct pressurized flow onto a wheel with buckets, called impulse blades affixed to the perimeter. Hydropower has advantages and disadvantages. Hydropower produces no CO2 nor particulate emissions. Being renewable and inexhaustible, hydropower is inexpensive. Finally, since water flows at all times, day and night, hydropower is dispatchable and reliable because it's not intermittent nor variable, at least in the short term. This being said, the startup costs for a hydropower facility are astronomically expensive. And I'm not sure if you notice this or not, hydropower has a nasty habit of inundating entire river valleys and all the trees, towns, animals, and archaeological treasures in these valleys under tons of water, not to mention altering fish migration patterns. Long story short, a dam and reservoir is a destructive beast that fundamentally alters the ecosystem in which it is built. Additionally, hydropower is very site-specific and subject to long-term drought conditions. Lest you think hydropower facilities be confined to rivers, there's an ocean of opportunity out there, including wave and tidal energy. Wave energy systems come in all sorts of crazy configurations, including point absorber buoys, surface attenuators, oscillating water columns, and overtopping devices. These different configurations convert wave energy into either airflow, water flow, or the relative motion between two bodies, and these forces are then converted to electrical power. Tidal power systems, in contrast, make use of daily tidal fluctuations, a result of the gravitational interaction between the Earth and the Moon, to generate power. Certain tidal power stations open a gate in a dam to allow a basin to fill with water during high tide, and as the tide recedes, the outgoing water is routed through a turbine, generating electricity. Now let's take a look at wind power. My man Abraham Lincoln perhaps said it best in 1860. Of all the forces of nature, I should think the wind contains the largest amount of motive power. As yet, the wind is an untamed, unharnessed force, and quite possibly one of the greatest discoveries hereafter to be made will be the taming and harnessing of it. Fast forward today, and wind power is indeed being harnessed and forms an ever-increasing share of renewable energy electrical power production. I'll have you know this particular lecture entry was perhaps the most difficult for me to write because I had to continually restrain myself from running away with it. Even operating with this conscious limitation, when I sat down and read the first draft, I realized 99% of it was about wind turbines and included all sorts of fascinating details, none of which was appropriate for an introductory lecture. So I cut all that unnecessary detail out and put it in another, actually several other lectures for later fascinating details and long-winded discussions about these topics. This is the briefest of brief orientations about wind power, but it'll do. Modern industrial wind turbines are known as horizontal axis wind turbine generators, abbreviated as HAWT. Where the generator is located at the top of the tower and the axis of rotation turns horizontally. As wind moves through the rotor, which is the combined hub and blades, it turns the low-speed main shaft, which feeds a gearbox that steps up the high-speed shaft to a speed more appropriate for generation. The generator consumes the rotating mechanical power of the high-speed shaft and produces electrical power. The electrical power output of the generator is transmitted down the tower to a transformer at the base that is stepped up to an appropriate voltage for delivery to a collector substation where the output of numerous turbines, i.e. a wind farm, is again stepped up to an even higher voltage for long-distance transmission. There are numerous different configurations of wind turbine generators, such as direct drive turbines lacking a gearbox intermediary that we'll examine in greater detail in later lectures. Modern wind turbine generators are fascinating electromechanical constructs because they must automatically regulate numerous actuators in response to often wildly fluctuating input conditions. Of primary concern are wind speed and wind direction. Wind speed directly influences rotational speed of the hub, and to keep generator output inside a desired range, the wind turbine actively pitches or changes the angle of attack of the blades using electrical or hydraulic actuators such that more or less of the blade is exposed to wind, thus capturing or shedding more or less of the incoming wind. Think of each blade as one uses a canoe paddle. Oriented in one fashion, maximum exposure is achieved, yet oriented in another, the blade slices cleanly through the water, or in this case, air. Additionally, the efficient capture of wind power necessitates a modern wind turbine generator be pointed into the wind. This necessitates a wind turbine know where the wind is coming from, where it's pointed at, and actuators known as yaw motors to effectively close the distance between the two. Turning a wind turbine generator into the wind is known as yawing. Pitching and yawing mechanisms, as well as other accessory mechanical and electrical systems, can additionally serve to de-energize the wind turbine for purposes of repair and service and emergencies. We'll examine wind turbine pitching and yawing systems and much more in greater detail in later lectures. As with any energy source, wind power has advantages and disadvantages. As with hydropower, wind power produces no CO2 nor particulate emissions. Being renewable and inexhaustible, wind power is inexpensive and essentially limitless. This being said, wind is an intermittent, variable, and non-dispatchable resource, and ideal wind farm conditions are site-specific and often located in rural areas or out at sea some distance from population centers where power is actually used. As with any power generation facility, a wind farm can alter the environment which is installed, principally because wind turbines are so visual and so obvious. Given the dispersed nature of wind resources, a large wind farm necessitates a lot of towers be erected to produce an appreciable amount of electrical power. While wind farms do necessitate some road building and heavy equipment during the construction phases, once constructed, wind farms can serve dual use, in that while the wind turbines operate, the land below them can continue to be farmed or used for other power generation purposes like solar farms. There's a lot of crazy, untrue complaints about wind turbines that I will not address here because they're crazy and untrue. But there are concerns grounded in truth that I will address with the intent of showing you these concerns might not be as big as you might be led to believe. I'll discuss a lot of these in greater detail in later lectures. Well, let's consider bird strikes for one. Wind turbines have been unfairly accused of being bird murderers, as if entire flocks of pigeons, peregrine falcons, plovers, peacocks, and penguins are continuously ground into a feathery pulp of plumage. Modern wind turbine generators are not giant bird blenders because they don't spin at a high rate of speed like some older designs that rightly deserved this condemnation. I'm not going to lie to you. Wind turbines do kill birds, just not as many as you think. In fact, it's probably a lot less than you think. Take a look at this chart illustrating the number of anthropogenic, human-caused bird mortalities in the U.S. Take a guess what number one is. Cats. Cats kill like 2.4 billion birds. What's the leading cause of bird death number two? Building strikes and windows at 600 million birds. Cars come in at number three with 200 million deaths. Collisions with power lines comes in at number 4 with 23 million deaths. Collisions with communication towers comes in at number 5 with 6.6 million deaths. Electrocutions from power lines comes in at number 6 with 5.6 million deaths. Apparently, U.S. birds don't die of agricultural chemicals, only Canadian ones. Go figure. And wind turbines, those come in as super distant 7th place at a paltry 230,000 deaths, essentially 0.01% of the pile of birds killed by cats. Now realize this chart is drawn using the logarithmic scale, where each equal vertical division is a power of 10. This is somewhat misleading, and it gives the false impression that if wind turbines just tried a little harder, or their blades were just a little sharper, or if they turned a little faster, they could be a contender. But this is far from the truth. If we drew this on a linear scale, you get the true picture. Wind turbines do kill birds, but vanishingly small compared to all the other more accomplished bird murderers out there. Get a grip, people. Put your cat on a leash. Again, I don't want this series to dive into public policy and prefer they're restricted to solely the electromechanical concepts of renewable energy, but realize All modern energy facilities now need to go through a regulatory siting process that considers environmental impacts and authorizes a specific take of unthreatened species as the price of doing business. All power plants have impacts, some more than others. Way back when, you could drop a 171-foot high, 2,690-foot long, 132-foot wide concrete plug right in the middle of the Columbia River, never once having to account for blocking the migration route of a major fish species that has shaped the economy of the Pacific Northwest since time immemorable. I'm not saying wind farms, solar farms, and dams have no impact on the environment, but what I am saying is that they might have much less impact on the environment than a coal-fired power plant, and certainly less of a need for the combined might of our country's military to prop up morally questionable regimes in the Middle East with no special affection for democracy to ensure our continued access to petroleum. Ask me how I know. What were we talking about? Oh yeah, birds. When you get right down to it, a lot of the overhyped culture war pushback to wind, and sometimes solar, is because they don't like the way it looks. And that's the one thing I can't argue with, since it's a matter of personal preference. Wind turbines, like dams and coal-fired power plants, are designed to produce electrical power, not look cool. The fact that an energy facility does or does not look like something you want in your backyard, somebody else's backyard, in the city, out in the unpeopled wastelands, or out at sea is not a consideration in their purpose and design. I'm amazed at the number of people that live in the Columbia River power system that never once notice the 48-mile Bonneville Reservoir backed up behind Bonneville Dam, the 24-mile-long Lake Celilo backed up behind the Dalles Dam, nor the 110-long Lake Umatilla backed up behind the John Day Dam, but are startled at the sight of a wind farm. When you get down to it, the dam is old news because it's been here since before most people were born, whereas the wind turbines are new and people might not understand new things. All right, we got to move on. Let's now talk about solar. Solar is radiant energy produced by fusion inside the sun. Every day the sun radiates more energy in one day than the entire world uses in 1 year. If only we could somehow intercept it and store it. The problem is solar is distributed over a wide reach, and the small amount of energy that actually received by a particular area depends upon the time of day, the season, the location, and cloud cover. Collectors of various forms are used to absorb solar power and put it to work in various fashions. Now, I did say at the beginning of this lecture I was going to try and concentrate on electrical power production from renewable resources rather than discuss direct or alternate use. The key word is try. Solar is way too tempting to stay on this narrow path, so I'll make an exception this time and wander off it momentarily and briefly discuss passive solar design and solar thermal water heating. Passive solar design. One of the simplest and cheapest ways you can heat your house in the winter and keep it cool in the summer is to point it towards the sun when it's cold and shield it from the sun when it's hot. In the northern hemisphere, the sun appears predominantly in the southern half of the sky. In winter, the sun appears at a low angle to the horizon, whereas in the summer, the sun appears at a high angle to the horizon. One way of passively heating and cooling your home is to ensure the southern side, i.e. the sun-facing side, is composed of a high percentage of insulated glass. During winter, the low-angle sun shines into the building, heats the well-insulated interior. During summer, the high-angle sun is blocked by a small overhang or an awning that prevents entry into the structure, keeping it cool. The key word in passive solar design is passive. Do it once and forget about it. No additional expenditures required, ever. This is obviously too much to ask of structures that are already built. However, the orientation and design of every new structure must take passive solar design into consideration. You'll be glad you did. Solar thermal. Solar thermal uses the sun's heat to directly heat water as opposed to an electrical intermediary. The solar collector, either an evacuated tube or a flat plate, is mounted on the roof of a structure or somewhere with good exposure to sunlight. When the collector is warm enough, a pump pushes heat transfer fluid through the collector, and the heated fluid is then routed to a heat exchanger inside a storage tank, which heats water, which can then be used for domestic purposes. Alternate configurations of solar thermal heaters, known as drain-back systems, exist that heat water directly rather than relying on a heat transfer fluid. As the name implies, when drain-back collectors are cold, the water is drained back into the storage tank, thus preventing damage to the collectors and pipes in freezing conditions. Admittedly, passive solar design and solar thermal are not means of making electrical power from solar. but they sure do help, since a majority of domestic energy consumption goes towards heating and cooling the interior of buildings and the nearly constant task of heating water. If you think about it, there's two ways to meet the power needs of society. Perhaps the most obvious way is to make more power. Another way to meet the power needs of society is to have less needs. If you can shift a majority, not all, of space and water heating to passive solar design and solar thermal, you need less electrical power. All right, let's get back on track and discuss electrical power production using solar resources. There's two basic forms: photovoltaic solar, sometimes abbreviated PV, and concentrated solar power, sometimes abbreviated CSP. Whereas traditional power generation often relies on an external prime mover turning a generator to produce electrical power, PV is different in that it consists of no moving parts and instead relies on a physical property of certain semiconductors that, when exposed to a certain wavelength of light, a tiny voltage differential is produced. Photovoltaic. Get it? Light-induced voltage. I will not bore you with the details here, but imagine a cell that produces a tiny amount of voltage and current when exposed to light of a given intensity. A cell is the basic building block of solar. When enough of these individual semiconductor cells are stacked in series, the voltage adds up. And when strings of these series stacked cells are connected in parallel, the current adds up. Such that a PV module or panel, being a series parallel connection of individual cells, produces a usable voltage and current for export. Series parallel connected collections of multiple PV panels are called PV arrays and produce larger values of voltage and current than an individual panel. Photovoltaic power is by its nature DC. This is fine if you want to directly drive a DC load like a DC light or a DC fan, or perhaps charge a battery using a charge controller, which is a device that manages the charge process such the batteries are not overcharged, undercharged, nor damaged. DC is great for DC loads and battery-based off-grid applications. However, certain accessory components are necessary to produce grid-compliant AC, principal among them being an inverter. An inverter is a power electronics device that converts the DC input of a PV array and inverts it into grid-compliant AC with the correct magnitude, frequency, and phase shift suitable for export. Smaller residential inverters produce single-phase AC, whereas larger industrial inverters produce industrial three-phase AC. Power generated by solar photovoltaic forms an ever-increasing share of renewable electrical power production, principally because the cost of producing panels has gotten so cheap. As I mentioned previously, solar farms are increasingly becoming co-located within wind farms, such that technicians servicing these farms need to understand both wind and solar, and batteries for that matter, since these energy storage facilities are also being installed with increasing frequency. Concentrated solar power, or CSP in contrast, is a lot like traditional generation with a prime mover and turbine, only the sun, instead of coal, natural gas, or nuclear power, serves as a primary source of heat to make steam. There's a couple different configurations, but two are worth mentioning specifically: the power tower and the parabolic trough. A power tower uses a tower, hence the name, in the center of a field of rotating mirrors that tracks the sun. As the sun moves through the sky, the field of mirrors reflects the collected sun onto a fluid-filled thermal receiver at the top of the tower. A parabolic trough, in contrast, uses a long reflecting trough that focuses sunlight onto a fluid-filled pipe located along the focal line. In both these scenarios, the sun-heated fluid in the reservoir or pipe is sent to a heat exchanger to generate steam and then used to generate electricity, as would a regular turbine driven by a thermal cycle. Or this heat can also be stored for later use. In this capacity, CSP serves not only as a means of actively generating power when the sun is in the sky, but alternatively as a means of potentially storing solar power for later use. Pretty neat, eh? The principal complication of CSP is that it is extremely site-specific and necessitates at all times the mirrors or parabolic trough be positioned at a precise angle for optimal focus and heat transfer. Solar, like other means of power generation, has advantages and disadvantages. Solar, like wind and hydro, produces no CO2 nor particulate emissions. Solar is well matched to meet the majority of power needs, since most of the non-zombie people of the world are awake during the day. This being said, solar is not a perfect match, and solar struggles to meet needs at dawn and dusk when the sun is low. It should go without saying that PV solar only works when the sun is shining, thus without storage cannot meet power requirements at night, nor during periods of heavy cloud cover. Given the dispersed nature of solar across the surface of the Earth, a large solar farm necessitates a lot of space to produce an appreciable amount of power. Solar panels themselves, although composed of no moving parts, can be damaged by extreme weather events like wind and hail and need to be regularly cleaned to operate at peak efficiency. Additionally, PV panels carry an upfront cost to the environment via their production. I'm not saying they don't. However, given a PV panel has no moving parts, they can offer renewable energy for the remainder of their more than 30-year lifespan. We'll examine PV solar power in greater details in later lectures. All right, that is our brief survey of hydro, wind, and solar power. These are the big three of renewable energy. At risk of being accused of neglecting biomass and geothermal, I should at least briefly discuss how these two other players fit into the larger pattern. Biomass is renewable organic matter that comes from plants and animals. If you think about it, biomass is stored solar energy in plant form. Biomass can be burned directly for heat, converted to liquid and gaseous fuels, or used to produce electricity. Biomass like wood and waste wood and residues from forestry operations, lumber, paper, and furniture mills can be burned directly or compressed into pellets and burned for space heating and cooking. Biofuels like ethanol and biodiesel are transportation fuels produced from renewable agricultural crops and food production wastes. These biofuels can be used in automobiles instead of petroleum. The major criticisms of biofuels is that cropland and resources that could be used for food production is instead diverted to grow biomass for fuel instead. Biomass can also be burned directly as the fuel driving a traditional steam turbine. Similarly, a waste-to-energy plant collects and burns biogas from landfills to produce electricity, or it can be cleaned up and used as a fuel directly. Geothermal energy is thermal energy extracted from the earth. This heat can be used to directly heat a building or water, or be used to generate electricity in a similar manner to a traditional steam turbine, only the heat from the earth, instead of coal, nuclear, or natural gas, drives the heat cycle. Unlike wind and solar, which are subject to the capricious whims of sunrise, sunset, cloud cover, and weather patterns, a geothermal plant can be a stable, reliable source of renewable energy and ramp up and down to meet immediate needs. Whereas the footprint of hydropower installations, wind farms, and solar farms can be huge, given the distributed nature of these resources, all the action of a geothermal plant happens below the surface, making it one of the most visibly unobtrusive forms of renewable energy. This being said, you got to find that perfect spot to put a geothermal plant, meaning geothermal plants are very, very site-specific and only work in geothermally active zones like New Zealand, Iceland, and certain hotspots in the US. There you go. Water, wind, fire, and to a lesser degree, earth. Now that our brief survey of renewable power generation is complete, let's summarize some of our findings and compare and contrast the means of generating power from renewable resources with traditional non-renewable resources. Beyond discussions of renewable versus non-renewable and clean versus dirty natures, there seems to be a common theme for most but not all of these various means of making power. Non-renewable installations typically don't take up a lot of space. They're dispatchable, and most of them are already built. This being said, most are becoming increasingly expensive to run as the finite nature of the non-renewable fuel that powers them becomes economically and environmentally expensive. There are notable exceptions to this general characterization. Renewable installations, in contrast, often take up a lot of space. Most of them are non-dispatchable, and most have huge upfront costs for installation. But they're becoming increasingly inexpensive to run. Again, there are notable exceptions to this general characterization. There's an additional feature of most renewable installations. A majority of these energy forms are site-specific, and ideal locations are often found in rural areas situated far from cities where power is actually used. This implies two important things. Renewable energy is largely a rural phenomenon and can bring jobs to rural areas. Number two, we need an updated grid that can transmit renewable power from where it's generated to where it's being used. All right, before we close out this lecture, I wanted to give you a quick snapshot of how the United States uses energy. At the time of this recording, our overall energy consumption looks something like this. Petroleum, 38%, natural gas, 36%, renewable energy, 9%, coal, 9%, nuclear, 9%. Now keep in mind, this is overall energy consumption, not the inputs to electrical power production. 70% of our petroleum inputs goes directly to the transportation sector, and really only 1% is directed towards electrical power production, the rest being apportioned to industrial, residential, and commercial sectors in various shares. In contrast, all or 100% of nuclear power is directed towards electrical power production. If we concentrate on just the inputs to electrical power production, the mix looks something like this. 40% of the inputs to electrical power is natural gas. 20% is coal. 18% is nuclear. 10% is wind. 6% is hydro. 4% is solar. And the other is 2%, which includes biomass, geothermal, and petroleum. This is again a national mix, and understandably there are regional variations. Now don't waste your time copying these numbers down because they change annually and won't be featured in any quizzes or tests. The real point of me including these diagrams is to emphasize a point I made earlier in this lecture. Electrification of the transportation infrastructure is going to happen, and its effects will be huge. Look at how much petroleum is being used to fuel transportation. If transportation isn't getting energy from petroleum, but rather from electrical power sector, where is the electrical power sector going to get that energy from? More renewables? More nuclear? More natural gas? More coal? More petroleum? That's stupid. The point being, electrifying the transportation sector will only be clean as the source of the electrical power sector. Don't trade a petroleum-powered transportation sector for an electrical sector powered by petroleum. Is the electric car something that's going to wreck the grid? Or hear me out here. Will the electric car save it? Think about it. One of the principal challenges of an all-renewable grid is storage, since wind and solar are intermittent, variable, and non-dispatchable resources. Building some large, centralized energy storage facility might be cost prohibitive. However, what if you had millions of small energy storage facilities distributed absolutely everywhere? From the perspective of the grid, every electric car is just a battery, a place you can store renewable energy in times of plenty. And here's where it gets interesting: withdraw in time of need. All right, on that note, that's all I got for you today. Good luck fixing this mess. You're going to need it. In conclusion, this lecture compared and contrasted non-renewable and renewable power generation and examined the basic functions, advantages, and disadvantages of wind, solar, hydro, geothermal, and biomass. Remember to review these concepts as often as you need to really drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.